Hi, so I'm Bryan. I am from the University of Pittsburgh, and this is joint work with Drs. Joseph Ramsey from CMU and Dr. Gregory Cooper also from the University of Pittsburgh. And this is on scoring Bayesian networks of mixed variables. Down is next. Okay, so as many of you may know, Bayesian networks constitute a graphical framework for representing probabilistic relationships. And we're interested in learning these networks because, given a few assumptions, we can interpret their structures causally. That is, if we have a variable A and a variable B in a network and a directed edge from A to B, then we can say A causes B. While much work has been done in the presence of purely continuous data and purely discrete data, very limited work has been done in the presence of both continuous and discrete, especially work that scales to hundreds of variables. And so the goal of this work is to provide scalable solutions for the discrete and continuous mixed case. So in my talk today, I want to start off by briefly going over the Bayesian information criterion. We're going to use this criterion as a framework for our two proposed scores. Then I'm going to go over our first score, the mixed variable polynomial score. Follow that up by the conditional Gaussian score. Then I want to quickly go over some adaptations we used and end on simulations and empirical results. So the Bayesian information criterion is a criterion used for model selection often, which approximates the log probability of a model M given some data D. And it can be approximated using the Laplacian method for integration as -2 times the log likelihood of a model plus the degrees of freedom times log n, where n is the number of instances in your data. To score a Bayesian network using this, what we can do is sum over BIC calculations for all nodes given their parents. So we'd fit a model for each node given its parents, calculate BIC, and sum over all of those. Okay, so going on to the first of our two scores, the mixed variable polynomial score. What we're going to do here is try to use higher order polynomials to approximate relationships between the variables in the network. In the continuous case, what this is going to allow us to do is use nonlinear relationships. And in the discrete case, we can approximate conditional probability mass functions using these polynomial functions. And essentially what we're doing here, to give you kind of an intuition, is we're approximating logistic regression, or multinomial logistic regression. And so after we have these approximations, we can calculate log likelihoods and degrees of freedom, and then score using the Bayesian information criterion. Okay, so since we're using the Bayesian information criterion, which scores a model given its parents, we're going to have two cases. One where we have a continuous child, and another where we have a discrete child. So the first of these two cases, where we have a continuous child, what we're going to do to score it is first partition the data according to the discrete parents. So what I mean here is we're going to, for all the discrete parents, we're going to look at all the assignments they take in the data and create a subset in our data set based on that. So all the instances where the discrete parents take a certain set of values becomes a subset. After we do this, for each subset in each partition, we're going to perform a regression, calculate a log likelihood and degrees of freedom term in each one of these partitions, and then sum them together for a log likelihood and degrees of freedom term for our full model, the child parent model. After we have those terms, we can score using the Bayesian information criterion. So to depict this, let's let x and y be continuous and a be a discrete variable with three categories. Here, x is a child of y and a, so we want to calculate the log likelihood of x given ya and the degrees of freedom of that model as well. So going through that procedure I just talked about, we're going to start off with some data. A has three values, so we're going to split it into three partitions. A equals 1, A equals 2, and A equals 3. We're going to fit regressions to each one of these. We're going to take the log likelihood terms and degrees of freedom for each one of these regressions, and sum them together to get our final log likelihood and degrees of freedom terms. Using these, we can score this case with the Bayesian information criterion. For the discrete child case, we're going to do something pretty similar, but we're going to start off by creating d binary variables of the child, where d is the number of categories the child takes. The idea here is we're going to kind of have like a one-hot representation of the child, where for each category, it's going to be 1 if there's going to be a variable for each category, and it's going to be 1 if the category is true and 0 if the category is false. Again, we're going to partition according to the discrete parents. And then we're going to perform regression in each one of these partitions. However, this time we're going to treat the regression lines as components to a conditional probability mass function. After we have this approximation, we can calculate a log likelihood and degrees of freedom, and then sum them together, and again score using the Bayesian information criterion. So going through this, let's let x be continuous and a be discrete with 3 values. Here we want to calculate the log likelihood for a given x and the degrees of freedom for a given x. So we're going to create 3 binary variables from a, a1, a2, and a3. Here we have a1 on the left is 1 when a equals 1 and 0 otherwise. On the bottom here, a2 is going to be 1 when a equals 2 and 0 otherwise, and the same for a3. We're going to fit a regression in each one of these, and we want to treat the values predicted from the regression as probabilities. So let's say in the first graph, where a equals 1, for any given value of x, we want to treat the value predicted by the regression as the probability that a equals 1. So right away, you guys probably realize there's 2 major flaws with this. We have axioms of probability which must hold. So for each one of these graphs, when we sum across for a specific given value of x, when we sum across the values of a given by the regression, it must equal 1. Additionally, for any given value of x, for any given value of a, we also need that they are non-negative. These are just axioms of probability that must be true if we want to treat these regressions as probability mass functions. Now, actually, based on how we've set this up, the first is actually true. However, the second, we run into some issues. It's true in the sample limit given some assumptions, but not in general. So we have to do something else. So what we're going to do is define a procedure that's going to shrink illegal distributions back into the domain of valid probabilities, and then we can use it. So again, here's our probabilities. Oh, and I'm not going to go over that. For the sake of time, I'm not going to go over that procedure here, but if you're interested, you can either talk to me offline or look up the details in the paper. So we're going to shrink these back into the domain of valid probabilities. And then we can use these each as a piece of a conditional probability mass function. So this is just those 3 graphs combined into one. The red line here is when a equals 1. So that's the probability that a equals 1. The blue is going to give you the probability that a equals 2. And the green is going to give you the probability that a equals 3. Using this, we can straightforwardly calculate a log likelihood and degrees of freedom for this model, a given x, and then pass these parameters, these terms, into the Bayesian information criterion to score this case. And that pretty much wraps up all MVP does to score a Bayesian network. So moving on to the conditional Gaussian score, the idea here is for any given instance in the data, what we want to do is to calculate a probability for that instance, move all the variables to the left of a conditioning bar and all the continuous variables to the left of the conditioning bar and all the discrete variables to the right of the conditioning bar. And what this will let us do is formulate our probability calculations in terms of partitioned Gaussian distributions and multinomial distributions. And once we have our probabilities in this formulation, we can straightforwardly calculate log likelihood and degrees of freedom terms. So to make this more clear, let's assume we have x and y continuous variables, and a being a discrete variable. And further, let's assume that y and a are parents of x. We can calculate the probability of x given its parents as follows, which we can rearrange such that the continuous variables are on the left of the conditioning bar and the discrete variables are on the right. And now what we have are two partitioned Gaussians where the ratio of them is going to give us our desired probability. So we still have that probability. Based off of that probability, what we want to do to calculate the likelihood, log likelihood and degrees of freedom for our model is calculate the log likelihood of the numerator and denominator, and then we can subtract them according to that to get our desired log likelihood and degrees of freedom. So for the first, x, y given a, we're going to do pretty much the same thing we did prior. However, this time, after we partition, we're going to fit Gaussians to each one of these partitions. This will give us a log likelihood and degrees of freedom term for each one of these, which we can aggregate together. So we have our desired log likelihood and degrees of freedom terms. And then we also have the denominator. We want y given a. So again, we're going to partition. We can fit a Gaussian to each one of these. And then sum them together to get our log likelihood and degrees of freedom term for the model y given a. Okay, so now we have the components we wanted. And using the formulation on the right, since division is subtraction in log space, we can subtract these to get our desired log likelihood and degrees of freedom terms, which we can then pass to the Bayesian information criterion to score our model. So when we're modeling a discrete child, we're going to do pretty much the same thing. Let's assume we have x, y continuous a discrete, and a is the child in this case. We can calculate the probability of a given its parents as follows, which we can rewrite in this way. Now we have partition Gaussians and a multinomial distribution. So now we have three different sets of terms that we're going to want to calculate. The first, we've already seen how to calculate this. We're going to partition, fit a Gaussian to each one of these. That'll give us the log likelihood and degrees of freedom terms. We can sum them together and get our total log likelihood and degrees of freedom terms. And then for the second two, we can just fit a multinomial for a and a Gaussian for x, y, respectively. And those will give us log likelihood and degrees of freedom terms. So now that we have all these terms, we can combine them according to the formulation in the top right. And that'll give us our desired log likelihood and degrees of freedom terms, which we can then pass the Bayesian information criterion to score our model. Okay, so given these two scores, I wanted to real quickly go over two adaptations we tried for them. The first of which is a binomial structure prior. So generally, when you're using the Bayesian information criterion, you assume the probability of all models equally likely and drop that prior probability of the model. In this case, we treated the addition of a parent as an independent random trial, and we modeled the prior probability of the model using the number of parents it had to calculate a binomial distribution, and hopefully that would give us a more accurate representation of what's going on. So this is an adaptation I'm going to be using in the results. And the second adaptation is a discretization heuristic, where what we did was in the case of a discrete child with continuous parents, we simply discretized the parents and used a multinomial to score this. And we wanted to see how that did. So for simulations, the first simulation we tried was based off of a conditional Gaussian model. What we did was we randomly generated sets of variables and edges. We specified a causal ordering over all the variables and edges, and over all the variables, and this directed our edges for us. And then in causal ordering, we simulated one variable at a time. For discrete children, we used multinomial relationships. We randomly parameterized multinomials. And for continuous children, we used partitioned linear Gaussian relationships. And for all simulations, we had 50% discrete variables and 50% continuous variables. And the discrete variables had anywhere between 2 and 5 categories. Those were also randomly chosen uniformly. Now, since MVP can handle nonlinear data, we also wanted to simulate some nonlinear data. So what we did was we changed the second step here to use partitioned polynomial regression with additive Gaussian noise. Using those simulations, we tested the following algorithms: the conditional Gaussian algorithm with the discretization heuristic, mixed variable polynomial with a linear basis. So that's not really polynomial, but it just used the linear term to do its approximations. Then MVP log n uses a polynomial basis from linear all the way up to the log nth degree. And then we also tested against using logistic regression for the discrete case with continuous parents. And we tried with the same base ECs we used for MVP to have a fair comparison. OK, so given those tests, given those scores, we used the following statistics. Adjacency precision, so that's whenever we say there's an adjacency, how often is that adjacency correct? Adjacency recall. Out of all the correct adjacencies, how many do we actually find? And then the same for arrowheads. So that's going to give us an idea of how we're doing in terms of directionality. We also looked at computation time in seconds. And all these statistics were averaged over 10 runs on a network of 1,000 samples. And as a search, we used FGES, which is just an optimized version of GES, which is a greedy search over the variables, over Bayesian networks. OK, so the first results I want to go over is looking at MVP versus just logistic regression. So here, the error bars are 95% confidence intervals. We simulated a network with 100 variables, average degree 4, using the linear simulation. And hopefully what you can see is that when you're comparing MVP and logistic regression using the same basis, there's not really much of a difference. Logistic regression does do a little bit better in some cases, but for the most part, the 95% confidence intervals almost completely overlap, and there's not a huge difference. However, if we look at the time, comparing MVP1 to logistic regression 1, there's about, MVP1 takes about 5 seconds, whereas logistic regression takes over a minute. And MVP log n takes around 10 seconds, and logistic regression log n takes about 220 seconds. So we have anywhere from 10 to 20 times speed up by using this approximation. And there wasn't much of a hurt in terms of the statistics. We couldn't really see a significant difference between the two. So then on nonlinear data, this is the same network simulation parameters, except using the nonlinear simulation. We see pretty much the exact same story. There's really not much of a difference at all between MVP and logistic regression, given that you're using the same basis. However, when you're looking at times, there's a huge difference. We're still seeing anywhere from 10 to 20%, or 20 times speed up. So going forward, I compared MVP with the conditional Gaussian score. And here, this is actually the same simulation, same data that was simulated for the first result. So you could compare the logistic regression to CG here as well. But I just concluded MVP log n since it seemed to do pretty much about the same as all the other ones, or better. So here, we can see that the conditional Gaussian variants, with and without the discretization heuristic, do pretty much as well or better than MVP, and therefore also the logistic regression. But in general, they all perform pretty well. And then in the nonlinear case, this is the same nonlinear data again that was simulated. We see kind of the same story but swapped. So MVP in this case is doing much better. However, conditional Gaussian, which without the discretization heuristic, it doesn't do too well in the nonlinear case. And this is because it's assuming a linear model when this is actually nonlinear data. With the discretization heuristic, it still does pretty well. And in general, they both perform pretty well on this data. So I also wanted to look at how they scale up. So this, I simulated a network with 500 measured variables, here with average degree 2, and compared them. So in this case, since it's the linear simulation, we see conditional Gaussian is doing, and its discretized variant are doing much better. Well, doing a little bit better, but MVP still does pretty well. And in terms of how long this took, for a network of 500 variables, it took conditional Gaussian and its discrete variant under 10 seconds. And MVP log n took about 1.5 minutes. So these are pretty highly scalable algorithms, and they seem to perform pretty well on the tests we've run. So in conclusion, we've presented 2 novel scores for learning Bayesian networks in the presence of both continuous and discrete data. The first of which is the mixed variable polynomial score. It scores pretty much the same as using logistic regression would, but it's 10 to 20 times faster. And it allows for more general class of relationships, such as nonlinear relationships. The conditional Gaussian score is quick and effective, and it works really well in pretty much any situation. Right, so both scores perform well, and we've scaled them up to networks of at least 500 variables. And they can easily be scaled to even more. And that's it.